JPL employee. I spent a lot of time at Caltech. And the NuSTAR mission has been a really fun project. It's about 150 scientists on the science team around the world. We have the Italian Space Agency have a big role in it. The Danish Technical University in Copenhagen had a big role. And then here's Columbia University, Berkeley, I guess. So it's been a fun ride with a nice, good team. I mentioned that we were a NASA small explorer. Just to explain to you in the astrophysics, so everything that NASA studies outside of our solar system counts as astrophysics. And the smaller line of that are these explorers. We have the mid-size explorers, and then small explorers, and then sometimes these mission of opportunities, which will often be NASA building an instrument on a foreign foreign telescope. And so there's NuSTAR, one of the more recent small explorers, and then I circled a couple other ones that came out of Pasadena that you might have heard of, WISE and GALEX and ACE. And so it's a really exciting line. It's had really exciting discoveries. And these missions are relatively small for NASA, so it's relatively small teams and relatively quick timelines from selection to launch. And in fact, by the end of this month, or maybe by the end of next month, the next SMECs will be selected. They do a multiple stage down select. So at this point, there's 3 missions competing for 1 slot. One of those 3s is called SphereX. It comes out of Caltech and JPL. So hopefully, maybe even next week, we'll find out that the next SMECs will be coming out of JPL as well, and you'll be able to hear a talk about that in a couple of years. Outline for the talks, I'll start off with a little bit of overview of what the NuSTAR mission is like, the engineering of it, the launch of it, and then I'll hit on those 3 science topics from the title of the talk. And here's the website, and here's the artist's conception of what NuSTAR looks like. We work in the high energy X-ray regime. So this is the same energy X-rays or energy light that doctors and dentists use to study your body, that airport security use to study your luggage. These are very penetrating light. They're able to go through material. We're not sending out X-rays and then studying X-ray images the way doctors do. Instead, we study some of the most energetic, powerful phenomena in the universe that create X-rays, like supernovae, the sun, black holes, and use that to understand the extreme universe. We work in the high energy or hard X-ray regime. I'll try not to use the term hard, but that's the first focusing X-ray satellite in orbit. Previous generations of X-ray satellites use something called coated aperture optics, which are like a pinhole camera, or I like to think of it as kind of have like a LED screen with lots of holes in it. And then the satellite's slewing across the sky, just rotating around. And you watch how the shadow pattern changes. You're able to figure out where the X-rays are coming from in the sky. And so that sort of design, this coated aperture optics, by nature gets you blurry images. You need really big detectors. You need this big LED shielding thing. And so it ends up being a very heavy satellite. I have a picture here of the European Integral satellite. NASA also has a coated aperture satellite up in orbit right now called the BAT Alert Telescope on the SWIFT satellite. Those sort of designs are pretty heavy, and if you're a NASA person, you know heavy means expensive. It costs a lot to launch things into space, so you try to make them as light as possible. NuSTAR instead does focusing optics, and X-ray focusing is a little bit tricky because if you had like your usual antennas like we see here, or like radio dishes you see, or normal optical telescopes, X-rays tend to like to go right into it and penetrate through. And so when you want to focus X-ray light, you have to do grazing incidence optics. So the X-rays come and you kind of nudge them, almost like a rock on a lake. And so our design is something called Ultra One optics. We have 2 bounces to the X-rays, and then it sends them down, focuses them on where we have our detectors. The optics end up, so rather than looking like a dish, it's a cylinder nudging the light in. And in fact, what we do is we have 133 shells, concentric shells, almost like Russian nesting dolls, that make up our optics. So our optics are about yay big. They weigh about 50 kilograms, and they focus the light in. Here's a picture from a Scientific American article about a year before we launched, a year and a half before we launched, where they took pictures of different parts of NuSTAR being built. And this shows you the top-end view of the optics. So you have these concentric shells, 133 of them, with little graphite spacers. This is a big effort to build this thing. And we actually built 3 of them. We launched 2 of them on the satellite. So this change in technology buys NuSTAR a huge gain. We're about 10 times, or even more than 10 times sharper images, about 200 times more sensitive images. And actually, because we weigh so much less than the other design, we're about 1/4 of the cost of the integral satellite, for example. So it's just a game changer in high energy astrophysics. Here's an example showing you what that change buys you. Here's an optical image of a nearby galaxy, NGC 1365. It's a barred spiral galaxy. The pretty picture is a ground-based optical image. And then what I'm showing you here is the beam size, or essentially the pixels, for some of the other high-energy satellites in orbit. So Integral has this big circle here. Swift's pixels are about the size of the full moon, roughly about 20 arc minutes versus 30 arc minutes. And then NuSTAR's beam size is about the size of Mars. And so we get much, much sharper images. We're able to, whereas Swift and Integral might have said NGC 1365 has a lot of high-energy X-rays coming out of it, with NuSTAR, you're actually able to map it. And so here's an example of another nearby galaxy, IC 342. Again, the background image is an optical image from the ground of this nearby spiral galaxy. The purple is the NuSTAR image of it. And we actually see 3 sources. You see 2 bright guys in the outskirt, and there's actually a little bit of high-energy X-ray light coming from the center of the galaxy. And so with Swift or with Integral, all the previous satellites just would have seen there's X-rays coming from this, and they would have known if it was 1 source, 3 sources, coming from the center, from the outskirts. So it's a total game changer in what you're able to do. That allowed it. So here's the optics I showed you. We have 2 of them, actually, just to get more collecting area. Just a fun little story. They sit in something called the trash can, or we called it the trash can before launch, till the guys who were building it said, "Can you stop calling it the trash can?" And yeah, had similar focal lengths for their telescopes, but they were billion-dollar class missions. They were able to launch on a big rocket, fully extended. For NuSTAR, we had to extend after launch because we had to go on a little cheap, less expensive launch vehicle. And so, we had this extendable mast that was built in Goleta, California, pretty close to Santa Barbara, by a company that specializes in extendables in space. They have about more than 100 things, some in orbit, some on Mars, with 100% success rate. The design for the one on NuSTAR was based on something that launched about 20 years ago on the shuttle, called the Shuttle Radar Topography Mission. And so it was a very similar design to that. And then here's just a sense of scale. Here's a picture towards the end of the integration and testing of NuSTAR. So there's the 2 optics modules. The mast is deployed in there, and there's a person, just to give you a sense of scale. So we're a little bit bigger than a person. Our launch was this interesting launch vehicle called the Pegasus launch vehicle. Here's a little video of it. This actually isn't our launch. We launched at night, and so this is just archival footage of a launch, but essentially they use an L-1011, a Lockheed 1011 jumbo jet as a first stage, takes the rocket up to 30,000 feet, drops it for 5 seconds, it ignites, and then takes you up into space. And so this all happened in June. The airplane took off from the Kwajalein Atoll in the Marshall Islands. And since that point, NuSTAR has been orbiting the Earth basically over the equator every 90 minutes and taking data the whole time. I heard on NPR this morning they launched Pegasus. They did another Pegasus this morning, if you had heard, with something called Cygnus, studying hurricanes. But there's beautiful videos of that. I just was watching that. So we get into space. First thing you do is you deploy your solar panel just to stay power positive. Exercise it, you're able to move the spacecraft around. And then about a week after launch, we deployed this extendable mast so that we could start focusing the X-ray light. And so this is the artist